the rocket will be having multiple gas turbines. Even in the aeroplane also, okay, if you see an aeroplane like this, there will be a wings, right? There will be a wings, and beneath the wings there will be an engine like this. Correct? Observed?
Yeah, sir.
Yes, yes.
So that is nothing but your gas turbine. Okay, it runs on something known as gas turbine, and it runs on the Brayton cycle. So this particular module will deal with the Brayton cycle and how many types of cycles are there, different types of cycles, and how to calculate its efficiency, what has to be done in order to increase its efficiency. So all those things would be dealt here. Okay, let us go one by one now. So gas turbine runs on the Brayton cycle. Its description and analysis, we will just look into it. Air standard cycle for gas turbine is the Brayton cycle. So gas turbine runs on which cycle? It runs on the Brayton cycle. The simple gas turbine consists of a compressor, a combustion chamber, a turbine. So we will just look into the parts of the turbine. We'll look into the parts of this gas turbine one by one. Okay. So what happens here is usually the arrangement would be something like this. Okay. It is a schematic arrangement, not necessarily it has to be in the same manner. So what happens actually is there would be a turbine like this. Okay. Inlet, there would be a wings if you are observed. Like this, there would be a wings. Okay. After that, there would be a outlet thrust like this. Okay. This is side over. So this would be a something known as a turbine. So inside there will be a many stages of things. Okay. So it will be something like this actually, but schematically it has been represented something like this. So what happens is initially the air would get compressed. Okay, there would be a compressor. There would be a compressor. Okay, so first the air would get compressed. Next, there would be addition of fuel. So fuel would be added something like this. A channel would be taken and it will be connected something like this. Okay, from which the fuel will be added and it's on, heats on because of the combustion chamber. Now the heat addition process takes place. How the heat addition process takes place, in what process the heat addition process will take place, we'll discuss one by one. Once the heat addition gets, next there will be a turbine. Okay, so the last and the important part of a compressor, sorry, of the gas turbine plant is your turbine. So I can call this as my turbine. Okay, this compressed. So at this stage I'm talking about, at this particular stage, what happens? The gas would be highly compressed, full of energy. Plus, it would be having a lot of heat because of heat addition. So high temperature, high pressure gas will just rush into the turbine, creating an enormous amount of torque. Creating the enormous amount of torque. Getting it? This is how the gas turbine works. Okay. So you can observe all these things are connected to a single shaft. The compressor, the turbine, the combustion chamber, everything is connected to a single shaft. So if turbine is the power generating device, isn't it? It gives out the power. So the power, it gives out the power. Whereas the compressor is, on the other hand, it is work absorbing device. It requires work to be done on the system. So therefore, if suppose say, if 100 kilojoules of energy is being generated by the turbine, 100 kilojoules of energy is being generated by the turbine, it would use 50 kilojoules of its energy to compress the initial gas because it is coupled to a same shaft like this. Getting my point? So this is how it works. We do not have a separate motor to run a compressor. Rather, what we'll be doing is we'll be using a turbine itself to run the compressor. Okay, that is how it works. That is what is being said here. Okay, a turbine, since the compressor is coupled with the turbine, it absorbs some amount of power produced by the turbine, about 50%, as I said, and hence low efficiency. So it has a low efficiency because you need to run the turbine also. You should run a compressor also, no? So that's why its efficiency is around 35 to 40%. So while calculating the problems on this, make sure your values is more or less within 40 or 45. Okay. The net work is therefore the difference between the turbine work and the compressor work. So if I told you, if the turbine is generating 100 kilojoules of work, and if the compressor requires 50 kilojoules of work, what is the net output from the complete system? How much work can I expect from this complete system? Yes? How much work can I expect? 50 kilojoules. So your whatever work output or net work output is there from the gas turbine plant, it would be the difference between the turbine work and the compressor work. Okay. Okay, so this particular turbine plant can be a open type or a closed type. We will discuss one by one. So we will just discuss what are the advantages of this particular gas turbines over the reciprocating engines, which we have just discussed in the last module. Reciprocating engines is nothing but IC engines. So what advantages we have on the gas turbine over compared to a reciprocating engines, which I'll discuss one by one. Number one is the mechanical efficiency is greater when compared to the reciprocating engines. Definitely yes. Mechanical efficiency when you compare, I'm not talking about the thermal efficiency. So this was nothing but, this efficiency is nothing but your thermal efficiency. You used to calculate, no, indicated thermal divided by, or nothing but the brake thermal. It is that particular efficiency. That is low. But mechanical efficiency is high just because it has nothing to do with reciprocating parts. There is no crank, there is no crankshaft, there are no cams, there are no rocker arms. All those mechanical components have just vanished away. There is single shaft which is running the whole thing. That's why mechanical efficiency would be higher for this particular kind of machines. Number two, gas turbines are steady flow devices due to the absence of reciprocating parts. Steady flow devices in the sense there would be a continuous flow from input to output. So and it would be a steady state in the sense it will be not having its turbulence within the turbine. So when you have that, there would be a stability inside the machine. Okay, reciprocating engines will give you a hampering effect, isn't it? So if you just sit in a bus which has just started, think you are sitting in a front end near the bus driver. So if this is a bus and if you're sitting here, okay, now if the driver starts the engine, okay, if driver starts the engine and he puts on its neutral on the idling condition and just leaves it, can you feel the vibration of it? Can you feel the vibration of reciprocating parts of an engine? How many of you have felt that? Isn't it? So that particular vibration is very huge, and such amount of vibration we cannot expect here. It would be very smooth. Okay. Overall weight of the machine per kilowatt is less. Definitely yes. If you want to generate such huge amount of power, which is required for an aeroplane or a rocket, using a reciprocating engine, then it has to be something of a size of a ship engine. Most of you have heard about the ship engines, right? There are very big, very massive engines. Okay, it has to be something of that order. Okay, again, you cannot achieve that amount of speed also. So I can say overall weight is very less for a power output. It's a single power output, and it has a high operational speeds, which is unbeaten feature of your gas turbine. High operating speeds. It operates at the speed of 3,000, 4,000 RPM. Okay, very great speeds and very massive speeds, which is a primary requirement to run your aeroplane or your rocket. Okay, this particular gas turbines are of two types. One is open cycle gas turbine and other is the closed cycle gas turbine. There is only one difference. What happens is, let us discuss now open cycle gas turbine. What happens is air is letting in. It is compressed from state 1 to state 2. Now air is getting compressed. At this particular point, it is a high pressure air for which heat is being added in the combustion chamber. Heat is being added in the combustion chamber and it reaches the state 3. At state 3, it is high pressure and high temperature gas. And this particular high temperature, high pressure gas is made to impinge on the turbine so that the turbine rotates. Okay. Once the turbine rotates, the low pressure, low temperature gas is being left to the atmosphere. Getting it? So this is the open cycle gas turbine. Now what happens in a closed cycle gas turbine? I will just see here what happens in a closed cycle gas turbine. Same process, 1 to 2 you are compressing the gas, and 2 to 3 you are adding up the heat. Okay. At particular 3 there is a high pressure, high temperature gas which is made to impinge on the turbine. This turns the turbine, gives out the necessary work output, and at the outlet you have low temperature, low pressure gas which is not being let to the atmosphere, but rather it is sent to a heat exchanger. This is the major difference between an open cycle gas turbine as well as the closed cycle gas turbine. So in the open cycle gas turbine, what we used to do? We used to let the outlet of the turbine to a, what you can say, atmosphere. Whereas in the closed cycle gas turbine, we will just get it back, okay, to the heat exchanger. So in the heat exchanger, what happens? This high pressure, this little bit of temperature would be there, not so high as compared to the state 3, but definitely it would be of some temperature that would be brought down to a normal temperature so that you can compress it again from the state 1. So just we are bringing back the state of the fluid back to the state 1 so that it can be compressed using an heat exchanger. So for cooling, either you can use air or you can use water depending upon the facility available for the turbine. Okay, so this is the difference between an open cycle gas turbine and a closed cycle gas turbine. So what is the major difference? In open cycle gas turbine, we are letting out the output of a gas turbine. Now, in the closed cycle gas turbine, we are not letting it out to an atmosphere. Rather, we are sending it back to a heat exchanger where it is cooled back and reused inside the system. Okay, where it is cooled back and reused inside the system. Getting it? So, any doubts here in the open cycle and closed cycle gas turbine? Any doubts?
No,
This is a simple question and an important question too. It has been asked many times. So there is a difference between the open cycle and gas turbine. I wish anyone could read it. Amok, can you just read the first point? Amok Hegade. Amok, not there.
yes, sir. Yes, sir.
Amok, first point ಓದು ಓಪನ್ ಸೈಕಲ್ ಗ್ಯಾಸ್ ಟರ್ಬೈನ್ ಅಲ್ಲಿ ಮತ್ತೆ ಕ್ಲೋಸ್ ಸೈಕಲ್ ಗ್ಯಾಸ್ ಟರ್ಬೈನ್ ಅಲ್ಲಿ ಒಂದಾದ್ಮೇಲೆ ಒಂದು.
Working usually air.
So working fluid is usually air in case of an open cycle gas turbine. For example, your aeroplane engine, your rocket engine is nothing but your air there, working fluid. Next, closed cycle.
Working fluid can be
Any
only
fluid, isn't
fluid.
it?
Yes, sir.
Any fluid in the sense it can be liquid also sometimes, okay? But rarely we use liquid since it is a gas turbine. We use a heavy gas for its operation of a closed turbine because we are just reusing it, right? Next,
Working
second
pressure
point.
is atmospheric pressure.
So working pressure is atmospheric pressure. Here, working pressure is
Working pressure is above the atmospheric
above the
side.
atmospheric pressure. Next one, third point.
Heat transfer coefficient is same, small.
Small. Here, heat transfer coefficient is large. So what do you mean by heat transfer coefficient is the ability of the material to conduct heat. So that is known as the heat transfer coefficient. That particular ability of the material to conduct heat is small in case of an open cycle, but in large in case of a closed cycle. Next point.
Wearing the load is difficult.
Wearing the load is very difficult. Here,
Wearing the load is easy.
wearing the load is easy. You can easily wear the load in case of a closed cycle gas turbine because you'll be having a control on that. But having a control on an open cycle gas turbine is really difficult because for every cycle of its operation, unknown pressurized gas would be entering the engine system. I mean to say the turbine system. So you cannot control the atmospheric air. So therefore, you cannot control your open cycle gas turbine. Next one.
Part load efficiency is poor.
So part load efficiency is pure and part load efficiency is good. We will get to know once you're done the what once you get the meaning of part load efficiency, then only we can explain this. So you'll get to know after you solve the problems. Next,
Plant size is larger.
plant size is smaller. So plant size is smaller just because in case of your closed cycle gas turbine, just because it can be coupled a bit and you can rotate a bit. Okay, in case of open cycle gas turbine, you require a huge amount of air to be compressed. Okay, so here your entire system is of a high pressure in the case of a closed cycle gas turbine. So when you are running at a high pressure, naturally you can compress the whole equipment setup. Okay, next, only good quality. Yes, next point.
Only good quality fuel can be used.
Here,
Inferior quality also.
fuel can also be used. I think it is self-explanatory. Next point.
Filtering of a incoming air is necessary.
So filtering of incoming air is necessary because for every time you are taking a fresh charge, fresh air you are taking it up. So therefore filtering is necessary here.
Filtering of air is eliminated due to closed circuit.
Okay, next one.
System is simple and cheap.
Yes,
System is complicated and so the
costly. Next one.
costly. Requires no coolant. Atmospheric itself act as a coolant.
Here.
Requires coolant and an heat exchanger.
Okay. This one.
Plant efficiency and power output is low.
Low. Here the plant efficiency and the power output is high. So these are the few differences. Out of all these 11 points, if you manage to write at least if you manage to at least write 5 to 6 points for a question of 4 marks, then it is more than sufficient. Okay. Next, we will talk about advantages and disadvantages of open cycle and closed cycle gas turbine. So above points can be written as for the same. I mean to say, if they are asking for advantages and disadvantages of open cycle gas turbine, you can just write all of this, isn't it? And if you are asking for closed cycle gas turbine, you can write individually all of this. Okay. So do I require to give advantages and disadvantages in a separate manner? Are you able to hear me?
Yes, sir.
Okay. So the same points can be written as advantages and disadvantages. Are you agreed upon this? Yes or no, man?
Yes, sir.
Okay. So we will next move on to joules after just 5 minutes. Okay, I need to attend a call. I'll come back after 5 minutes. Later, we will discuss what is uh, the Breton cycle. So we will see how exactly the Breton cycle looks. Okay, so I will just come back within 5 minutes. Okay, guys, we will discuss about the Joule cycle in the next class. Okay, so I need to go. I have some bit of work. So